Hello students, welcome to your final videos up here. Woo! Go Courtney!
Now you should be super excited, your audience is. Let's go ahead and make sure you get your final date, time, location, parent, guardian sign off. We have a few review problems here, and we're going to follow shade-base equations. Circle chart. So we come over here. Step number 1, it says to shade the base. Let's shade our base here. We've done that. Check. Then it says here to find the area of the base. So let's trace it. And come over here and ask yourself, how do you find the area of that shape? And you should have gotten apple pie is really, really good. So we go here, and our radius, we're going to circle it. That's 5 squared. So we have a capital B here is 25 pi. You check for units. You don't have any, so we're just going to use the U, and it's squared. Box that. That's your B. Now here, let's go ahead and trace. We want the altitude, which goes straight down at a right angle. Notice we don't have that. But let's look at what we do have. I like you to trace up the slant height, down the true height, and across. Ask yourself what you got there. You should notice it's a right triangle. Let's pull that out so we can see it. That's 15, our unknown height, and that's a 5. Have 2 sides, need 3rd side. Pathetic. Good deal. So in the margin, let's do this longhand. Do your own math there. Okay, I'm going to want this in exact radical form. So that root 200, we're going to factor out. Now let's look for our dates. We have a pair of 5s. We have a pair of 2s. That 2 has no date, stays home. So your actual height here is going to equal 10 root 2. Box that. That is your true height. This is a cone. So volume is 3 dimensions. Therefore, the fraction of a prism to a pyramid is 1/3. So we come down here, and our volume equals capital B times height over 3. Circle, plug, chug. Base, base, height, height. We simplify. Outies talk to outies. Innies talk to innies. And if it's in simplified version, you leave fractions as they are. So those outies are going to talk to each other. So 3 doesn't divide into anything, so we're going to end up with this. Watch how we do this. We stick pi at the end. Units cubed. And that is what is called exact form. Exact form, by definition, uses radicals, is a fraction, and pi form. No decimals. If it says exact, there's no decimals anywhere, because decimals are not exact. All right, I want you to take just a moment. I want you to write 2 things that you want to remember about this problem. Write 2 things that you want to remember about that problem. Pause the video, Write two things and then come back. All right, students, there is your review. Let's check on here. Now we're going to do another review, concept of similarity. And similarity means this. Copy this down. Similarity means things that have congruent angles and ratios equal. Congruent, similarity means congruent angles, ratios equal. We studied that way back around Christmas time. And that's the technical definition. The slang definition are solids have the same shape, but just a different size. Similar solids have the same shape, different size. Now, to test for similarity, we check the RE part, which is ratios equal. So we're going to see if the ratio is equal all the way around. So let's trace together. Ready? Trace that 3 and that 15, and we're going to reduce left to right. That's a 1 to 5 ratio. Now trace the 8 and trace the 40. I'll look it up, buddy. Okay, so this we also know 8 goes into 40 1 to 5 times. Let's try this one, 5 to 25. And let's check that. 5 to 25 is 1 to 5. So notice, all the ratios are equal, so we would call these solids similar. And so my big fat yes, they are similar, because the ratios are equal. Okay, so let's check another one here. Check our ratios, starting from here. Let's trace that 42 to 6, and you want to reduce that. We know 6 goes into 42. How many times? Okay, so this is going to be a 7 to 1 ratio. And let's try this one. This 56 and this 8. All right, students, you should have known, and that, of course, 8 does go in the 56, so you're going like this. That is also a 7 to 1 ratio. So our ratios are equal. So big fat, yes, they are similar. So that's how you determine similar solids. Let's try these two. I want you to try on your own. Those two on your own. Pause the video, do your own work, and then restart. Okay, students, let's see how you did here. We had 15 and 25. 5 goes in there 3 times. 5 goes in there 5 times. And then if we go like this, 9 and 12, 3 goes in there 3 times. 3 goes in there 4 times. Notice, for the RE, the ratios are not equal, so these are not similar. You should have gotten there. Let's check these guys. There is a little bit of a trick here. Watch out. Let's go slantite to slantite. That is a 1 to 5 ratio. Slantites to slantites. Ready? Let's do radius to, careful there, radius. If you did 10 to 100, you were wrong. And the reason is 100 was a diameter. We have to go radius to radius. And in that case, that would be 10 to 50, which again is 1 to 5. So this was a yes, they are similar. So those of you who said no is probably because you didn't physically trace the radius. Remember, everything is a brain is in your hand. Now, before we go on to our next concept, we need to review dimensions. The first dimension is something that just has length. That would be like a segment. If I said AB is 10 centimeters in length, that would be one dimension. Okay. And the second dimension, that has something that has both length and width. In other words, it's area. So that would be like finding the area of a square. That's 2 dimensions. Three dimensions is something that has both length, width, and height. That would be what we're studying right now, which is volume. If I asked you to find the volume of the cylinder, that would be a 3-dimensional concept. So 1 dimension is just length, 2 dimension is area, 3 dimensions is volume. Here's a very, very simplistic but important concept. When you change dimensions, you change ratios. When you change dimensions, you change ratios. When you change dimensions, you change ratios. This happens when you do unit conversion. Watch very, very carefully. Okay, so 1 yard, we know that 1 yard, if we have a 1 yard here, lengthwise, how many feet is 1 yard? That's, I mean, one, two, yes. So we know that 1 yard conversion is less than, but that conversion, and that's the one you've learned since you were just a kid, that conversion is only in the first dimension. When you go into the second dimension, a yard squared looks like this. You have a yard by yard. So it's 3 feet going this way, 3 feet going this way. So 1 yard squared is actually 9 feet squared. So a squared yard is 9 feet squared, not 3. When you change dimensions, you change ratios. If we were to come here and we were to cube a yard, in other words, we'd be 1 yard by 1 yard. And then our depth of 1 yard, that would be 3 feet this way, 3 feet this way. Now imagine those are cubes, and then if we were to go backwards, you would see what happens there. We'd end up with 27 sugar cubes there. 27, because if there's 1 layer is 9, you'd have 3 layers there. You'd end up with 27 feet cubed. So the concept is when you change dimensions, you change ratios. So watch what happened here. In the first dimension, it was 1 to 3. In the second dimension, it was 1 to 9. In the third dimension, it's 1 to 27. Notice what happened here. If this is x to the first, y to the first. Second dimension, x squared, y squared. Third dimension, x cubed, y cubed. You need to see that. If you take 3 and square it, ask yourself, what do you get? If you take 3 and cube it, ask yourself, what do you get? When you change dimensions, you change ratios. Let's see how this works practically. Let's take a single unit cube. Okay, so it's 1 unit going this way, 1 unit going this way, and 1 unit going this way. And now we're going to double the edge length. So we're going to take that edge and we're just going to double it. So from 1, we're going to go to 2. So we're just taking that edge and doubling it. I'd like you to predict, just predict, if we double the edge length, what do you think is going to happen to the outer area of that cube? And what do you think is going to happen to the volume? I'm going to pause for about 20, 30 seconds. I actually want you to predict. If we double the edge length, what do you think is going to happen to the surface area, which is like wrapping paper around it? And what do you think is going to happen to volume? I'd like you to actually predict there. Do this now. I actually want you to predict it. So if I double this edge length, what do you think is going to happen to the volume? What do you think? Take a look. I double the edge length. What do you think is going to happen to the volume? Pop that in the train. You're welcome. You're welcome to say it. Say, go ahead. Predict. Alrighty, so scale factor is the ratio of the sides simplified. So our scale factor is 1 to 2. The reason is this is 1 unit and that's 2 units. So our scale factor, which is 1 dimension, is going to be a 1 to 2 ratio. We're going to call that x to the first, y to the first. Now let's actually find what's called our surface area. So think of wrapping paper here. The surface area of the small one, okay, think of the outer squares. We have 1 outer square here, 1 outer square there, 1 outer square there, then a bottom, front, back. That gives us 6 squared units total. So the surface area of our small cube is going to be 6 units squared because we have 6 spaces like a die and they're 1 unit each. Now in our large one, this is 2 units this way, so look here carefully. So we have 4 squared units per face times 6 spaces. because you have a front, back, top, bottom, left, right. So our total surface area is going to be 24 units squared. Let's take that down to a ratio. 6 goes into 24. How many times? Okay. Yes. Okay. Your ratio, 6 goes into 24. That's a 1-to-4 ratio. So if you look carefully, that ends up being, we took that, if you square 1, you get 1. If you square 2, you get 4. So technically, we have x squared, y squared here. Now let's do volume. So down here, we're going to do volume now. And the volume of the small one, this should be volume. The volume of the small is base times height. Our base is 1 unit, and our height is 1. So our volume of the small is going to be 1 unit cubed. But the volume of the large, if you were to count cubes, think of it as sugar cubes. Technically, there'd be 1 cube in the front, 1 cube in the back, 3, 4, 5, 6, 7, 8. There is a total of, the volume of the large is 8 cube units. So our volume ratio was 1 to 8. If you look very carefully, what we actually have going on here is x to the third, y to the third. How do I know that? See that? If that's our x. All right, so, and because if I go here, if I go 2 times 2 times 2, that gave us the 8. So when you change dimensions, you change ratios. Let's do a couple practice problems with what this looks like. Are you ready? Couple examples here. Finger tap and read with me. Your mom and dad have cylindrical mugs with the dimensions to the right. Your first job is to ask yourself, are they similar? Let's check the ratios. Let's check the ratios here. So left to right, that's 6, that's 4. 2 goes in there 3 times, 2 goes in there twice, so that's 3 to 2. Let's check this way, our diameters. 2 goes in here 3 times, 2 goes in here twice. So notice the ratios are equal. The first question is, yes, they are similar. Second thing says, if they are similar, find the scale factor, the ratio of the surface areas, and ratio of the volumes. Watch very carefully. Learn to do this in the margin. We're going to write 1D, 2 dimensions, 3 dimensions. Our first dimensional ratio is going to be 3 to 2. Our second dimensional ratio is going to be 3 squared to 2 squared, which comes 9 to 4. And then our third dimension ratio is going to be 3 cubed to 2 cubed, and that's going to be 27 to 8. Now we're going to find the actual volumes. We're going to see what happens here. Okay, so for the actual volumes, let's do the dad first. We're going to go base times height. So we're going to do base times height. I'll show you a little trick. We're going to do the smaller mom one. I'm going to show you why you don't actually need to do the dad. I'll show you in just a moment. So the smaller mom, your radius is 1, and your height is 2. That's because your diameter is 2. So our base is pi r squared. That means our radius is 1 squared. And our height is 2. So the volume of the mom mug is simply going to be 2 pi inches cubed. Now there's a shortcut for the dad mug. Our volume from left to right is 27 to 8. Notice this is volume, so watch what I do. I can do like this. 27 to 8. Why am I choosing this? Because this is our 3D ratio and we're working with volume. Equals our actual volume is 2 pi. We can come up here and we can find that volume in pi form. We're going to cross multiply and solve. We're going to divide by 8 here. 2 goes into 8 4 times. So the actual volume of dad is going to be this. It's going to be the volume of the dad mug is 27 over 4 pi inches cubed. And this was 2 pi inches cubed. And we did that. We didn't even have to do the math because we can use this ratio. Let's try another one. It says the ratio of the areas. Above the area, we're going to write 2 dimensions because area is a 2-dimensional concept. The 2 prisms is 25 to 49. And what is the scale factor and what would be the volume? Okay, come down here and write 1D, 2D, 3D. Your 2D volume is going to be 25 to 49. That's your 2D volume. And then we're being asked to back that to this way. Best way to look at is that we have x squared equals 25, and we have y squared equals 49. Ask yourself, what was x and y? That's going to be x. Right? And we find that our scale factor is going to be 5 to 7. That's your x and y. 3D, bring it down. That's going to be x cubed, y cubed. We're going to go 5 cubed and 7 cubed. You get out a calculator if you need to. That's going to be 5 times 5 times 5 and 7 times 7 times 7. Get out your calculator and get those ratios. I'll give you about 30 seconds to do your own math there. Keep track of me? You doing it right? Okay, let's do another one. And then we're going to solve. That's the one you're going to do on your own. Ready? So 3 says the 2 cylinders are similar. So the similarity sign. The ratio of the areas is 15. Above the word area, we put 2D. Instantly, we know this is x squared and y squared. I'm asking what the height of the wall of the pyramid is. Height, you just trace it, that's 1 dimension. So if right here, my ratio is going to be 16 to 25, and my smaller, I'm going to bring it around this way. Let's square root and let's get our ratios of our heights here. Square root both sides. End up with 4 to 25. Excuse me, 4 to 5. And we're going to go this. We have an unknown height over 24 equals, our 5 is the larger one, our 4 is the smaller, and you simply cross multiply. Let's do one more, see if you guys understand this. It says, the two similar solids, the ratio of the volume, notice the word volume, is 343 to 125. Now volume is 3D. So the first thing you need to do is get all three of your ratios. 1 dimension, 2 dimension, 3 dimension. We're given our 3-dimensional ratios. To find our variables are all just lengths. That's going to be 1 dimension. So you have to ask yourself, what number times itself 3 times is 343, and what number times itself 3 times is 125. I'm going to pause here. I want you to figure out, using a calculator, there are whole numbers, find out what those are. Alrighty, now if you check those, you should have figured out that this was 7 times 7 times 7, and that this was 5 times 5 times 5, which means our first dimensional ratio is simply 7 to 5. That's called your scale factor. We went from 3D back to 1D. So now we're going to use that to solve for our variables. We're going to do like this. Ready? We're going 7 to 5. So x over 10 equals 7 over 5. Cross multiply. Notice I didn't say 70 though, because the key to multiplying is not to multiply. You get x equals 14. Let's try this. Let's try this. This one's 7. Automatically, you know this one is going to be 5 because it's a 7 to 5 ratio. And then we want this to be 7 to 5. So ask yourself, 7 is 5 times, so 5 times 5 is 25. So we started with 3D and we went backwards to 1 dimension. I want you to try these two on your own. Pause the video and then restart. Okay, students, let's see how you did here. So it says right here, the scale factor, underline the phrase scale factor, that's 1 dimension, is 2 to 3. So that means we have x to the first, y to the first. The volume of a smaller solid is 16 units cubed. What is the volume of the larger solid? Volume is 3 dimensions. That's very important. We're going from 1 dimension to 3 dimensions. So we're going to start here by doing our ratios. 1 dimension in the margin, 2 dimensions, and 3 dimensions. Our scale factor, we already have our 1 dimension. Our x to the first, y to the first, is going to be 2 to 3. Our second dimension is x squared and y squared. That's going to be 2 squared, that's 4, and 3 squared, that's going to be 9. Our third dimension is going to be x cubed, y cubed. So we ask ourselves 2 times 2 times 2 That's 8. And then 3 times 3 times 3, that is 27. That's our 3D ratio. Now we're going to go small to large. Our small volume is 16 units cubed. We want to know our large volume. So the question is, which ratio are we going to use over here? You should have noticed volume is 3D, so we use our 3D ratio, which is this one. When you change dimensions, you change ratios. We're going to cross multiply. And then you simplify. So 2 times 27, that's 54 units cubed. And the reason why we did that one is because we were told volume is 3 dimensions. Therefore, we use the 3-dimensional ratio. Last example of the year. Below are 2 similar solids. And we are told that with the volume ratio, 3D, of 8 to 27. Now that's volume, so that's 8 cubed, y cubed. The base lengths are equal to the heights, and that means that y is going to be the same as that height, and this x is the same as this height. And we're going to answer these questions below. First off, what's our scale factor? Let's get our ratios. 1D is x to the first, y to the first. 2 dimensions is x cubed, y cubed, squared. And 3 dimensions is x cubed, y cubed. So we have to work ourselves backwards. This 8 to 27 is in 3D. So we have to work backwards and ask ourselves, what number times itself 3 times gave us 8? And this is what number times itself 3 times gives us 27. You should have figured out here that your 1-degree ratio is 2 to 3, which means our 2-degree ratio is going to be 4 to 9. So our scale factor is right here, 1 dimension, 2 to 3. What is the ratio of the outer surfaces and areas? That's going to be 4 to 9. And we want to find h, x, and y. So that is just length. H, x, and y is length to length. So we're going to use 2 over 3 equals 8 over unknown h. Cross multiply. So we just figured out that h is 12. If h is 12, x is 12, and y is 12. W and Z, if you go like this, you can see you have right triangles. Let me pull these right triangles so it's a little bit easier to see. That's going to be 8, 4, and W. And that's going to be 12, 6, and W. And you want to solve there, Pythagorean theorem. That's going to be 4 root 5, because that's 16 root 5. Let's try this one. That's 180 equals W squared. We square root. You want to factor that out. And that's going to be 2 and 90, 2 and 45, 5 and 9, and then 3 and 3. Ask yourself who comes out, a 3 and a 2. That's going to be 6 root 5. Find the volume of the pyramids. That's simply area of the base times the height over 3. So our area there would have been 12 squared times our height, which is 8 over 3, and the volume here So the volume of the larger is 576. To get the volume of the smaller, we simply do our volume ratio, which is going to be 27 to 8. Cross multiply and solve. I'll be looking for your final answer on your paper.